All right, 16.6, Hückel's rule of aromatic or anti-aromatic compounds. All right, it's really, it's pretty simple. There's a simple equation that you have to follow depending on how many pi electrons you have that determine if it's aromatic or anti-aromatic. Okay, once the aromatic criteria are met, Hückel's rule then applies. Now, when they say this term aromatic, in this case, they're really saying once the criteria of the three criteria. So keep remembering these three criteria: cyclical, conjugated, and planar. Now, you might be asking yourself, how do you know if the molecule is planar or not? The only way to really know is to make the model. You're going to assume the molecules are planar unless you're told otherwise. Right, an 8-membered ring is not planar. So I'll tell you that right now. Anything, and there are actually rules later on in here that kind of tell you that. Pretty much once you go above 8-membered rings, your compounds are no longer planar. It's really, you know, 4, 5, and 6, and like 7-membered rings are kind of the planar ones. Anything above that are kind of not planar. But if you're told otherwise, assume it's planar unless you're told otherwise. Okay, but I'll kind of show you some other rules that will actually help you in order to do that. Okay, so once these three things are met, that's what they mean by aromatic in this case. You then have to go to the fourth criteria, which is trying to figure out Hückel's rule to determine if it's aromatic or anti-aromatic. Okay, and there are two equations. One, if the number of pi electrons equals the 4n plus 2, the system is aromatic, where n is an integer. Let me first get through the words and then we will talk about what this means. But basically it's your pi electrons. How many pi electrons are in your molecule? Okay, if the answer is 6, let's say you have 6 pi electrons. 6 equals 4n plus 2. Okay, if you solve for n will equal 1. As long as your n comes out to be a whole number, then that compound is aromatic. Okay, the 1 doesn't even do anything. I mean, it's not like the 1 means anything. As long as it's a whole number. If it's a fraction, then it's not going to follow that. It's going to follow the 4n rule. If the number of pi electrons equals 4n. So for example, if you've got 4 pi electrons, in that case 4 equals 4n, where n equals 1, which is a whole number, then you're in the anti-aromatic. It's not as stable. Okay, so a hint here is Hückel's rule is commonly used to determine aromaticity and anti-aromaticity. A continuous planar ring with overlapping p orbitals is required for the rule, otherwise the system is non-aromatic. Okay, so let's look at some examples. Okay, here's an example again. 8-membered rings are not planar. You see how this molecule is not planar? They kind of show you that they go up. So you don't have, technically, yeah, it's conjugated, but conjugated really implies that the electrons are able to flow around. Okay, so there's a little bit pi overlap. Okay, so this does not follow. I'm sorry, in Hückel's rule, it follows a 4n rule. Okay, let me show you. So remember, we have 4n plus 2, or we have 4n. Okay, so how many pi electrons on there? I'm looking at all the pi bonds. Here's a pi bond, here's a pi bond, here's a pi bond, here's a pi bond. So this has 8 pi electrons. Okay, how do I get 8? Well, there's 2 in this pi bond, 2 here, 2 here, and 2 here for a total of 8. So if I set these equal to 8 and solve for n, okay, this one will equal 6 over 4, which obviously is 3 halves, which is not a whole number. In this case, n equals 2, where it's a whole number. Okay, so it's following this equation, which is the 4n equation, which is anti-aromatic. Okay, so this molecule would be considered anti-aromatic because it follows the 4n equation, not the 4n plus 2. 4n plus 2 is for aromatic, 4n is for anti-aromatic. Okay, now in this case it's non-planar, so it doesn't even you know, fit that criteria, but I kind of wanted to show you how the last equations fit in here. Okay, so let's look at some of the annuals. 4n annual is anti-aromatic. Why is it anti-aromatic? Because it fits the 4n rule. Okay, 8-member annuals would be aromatic, but they're not planar, so it's really considered non-aromatic if they're not planar. If you assume it's planar, then it's considered anti-aromatic. Okay, 10 annuals is aromatic, except for isomers that are non-planar. Okay, for a 10 carbon, you can have lots of kind of possibilities, because then you can start having cis and trans type of pi bonds in there, which actually change things. We're not going to look at them too much. Okay, larger 4N annuals are not anti-aromatic because they are flexible enough to become non-planar, so they would just be non-aromatic. Okay, so in the case of this, what is that? How many? I don't even. That's 10. So here's the example we're talking about cis and trans. If they're all cis, this is non-planar, so it's not even aromatic. It'd be considered non-aromatic. Okay, if you have cis and trans like this, okay, again, it's not planar. It's going to be non-aromatic. How do you know it's not planar? You would have to make the molecule. Naphthalene, which has a bond in between them, this is conjugated. It's two like benzene rings hooked together, so it's an aromatic compound. Okay, it also has 2, 4, 6, 8, 10 pi electrons in it. So 10 pi electrons equals 4n plus 2. So if you solve for here n equals 2. So it fits the 4n plus 2, so this is an aromatic compound. It's planar, it's conjugated, it's cyclical, it follows the 4n plus 2. Okay? Just a few examples. 16.8, so hopefully you understood that. If you have questions, we will talk more about that in class, but just remember the 4 criteria: planar, conjugated, cyclical, 4n plus 2, or 4n to be anti-aromatic. Ions can also be aromatic compounds. Okay, I'm not going to worry about this. Let's not worry about that kind of a diagram. Okay, but what we're looking at is a cyclopentadienyl cation and anion. So what is that? Cyclopentadienyl cation is a 5-membered ring with a plus charge, and the anion is a 5-membered ring with a double bond, lone pair, and a negative charge. Okay. So the question is are these aromatic compounds? Can you do aromatic compounds with these? And the answer is yes, you can, because all you need are those 4 criteria that we talked about. Planar, are they planar? Both of these compounds are planar. Okay. Are they conjugated? Okay, remember, conjugated means alternating pi bonds, or every carbon has alternating pi bonds, which they all do. Here's actually the diagram. All right, you have all the diagrams right here. So you have these overlapping electrons. Is it cyclical? Yes, they're cyclical. And then now comes the 4th criteria, 4n or 4n plus 2. Well, the cation follows a 4n rule, right? There are 4 pi electrons here. So it fits the 4n. So this compound would be anti. This one has 2, 4, 6 pi electrons. So this would follow a 4n plus 2 system. So even these compounds, cyclopentadienyl anion is actually an aromatic compound. All right. So the cation has an empty p orbital and 4 pi electrons, so it's anti-aromatic. And the anion has a non-bonding pair of electrons in the p orbital, giving it 6 pi electrons. Therefore, it is aromatic. Okay. So you can have molecules that have charges that are not, an annual. These technically are not annuals because they're not alternating pi bonds. You have charges on them. Okay. Another interesting thing is we've talked about the pKa of a sp3 carbon. That's an sp3 carbon with a hydrogen on it. Okay. So we talked about last semester that sp3 carbons, okay, the pKa's, can you remember roughly what they were? You think about it? Somewhere between 45 to 50. It was like the highest pKa number that you can get. That's like the most non-acidic thing. But notice, this is an sp3 carbon. These hydrogens have a pK of 16. I mean, we are 10 to the 30, like 10 to the 30th times more acidic. I mean, that's huge. Okay, well, why is this sp3 carbon so acidic when I told you, well, a standard sp3 carbon on on ethane, let's say, is 45 to 50? Well, it's because it forms an incredibly stable anion. it forms an aromatic compound. Okay, you're going from a non-aromatic compound to an aromatic compound. This is as acidic as like water. Okay, how easy is it to pluck a hydrogen off of water? Well, you just need some sort of strong enough base, which in this case is a tert butoxide, and you can pluck off that hydrogen just like water. All right, so this, now that you're making something aromatic, you can it starts affecting the chemistry of these compounds, the acidity of the compounds. Right? Notice this is kind of a shorthand of showing that compound. Right? These electrons are resonating around, giving you the circle with the minus charge. Okay, so pretty interesting. All right, so by deprotonating the sp3 carbon on the cyclopentadiene, there will be a pair of electrons on the sp3 orbitals, so it can rehybridize to a p orbital. The 6 electrons in the pi can be delocalized over all 5 carbons, and it would make the compound aromatic. Okay, so aromatic is not just, it's not like, so here I have an sp3 carbon that I turned into, a hybridized carbon. Okay, here's again the orbital view of the deprotonation of the cyclopentadiene, sp3. When you deprotonate it, you kind of get this p orbital where the electrons now are able to resonate around into the molecule. All right, so deprotonation will allow the overlap of the p orbitals. Cyclopentadiene is not necessarily as stable as benzene, and it actually reacts as if it was a negative charge. So it's not as stable, and you can probably figure out why it's not as stable. Think about it. Why is it not as stable as benzene? Because it has a negative charge. It still has a negative charge. Sure, it's aromatic, but it has a negative charge. We talked about that things want to have a neutral charge. If it's not neutral, it's a little bit more unstable than its original state. Okay, so it's not as stable as benzene. So, and it does react as a nucleophile. So I can take this carbon and start adding it to like a carbonyl and other things, and it still reacts SN2 fashion, but it also is an aromatic. It will also act as an aromatic compound. Okay, cyclopentadienyl cations are not very stable. All right, you would think that if you took this compound, the cyclopenta-2,4-diene-1-ol, put it in acid in order to eliminate it to form a cation right here, you think, hey, if I form a cation right here, such as this compound, I can form resonance structures. But what's interesting is that this compound isn't formed. You think, well, why not? You can have, it should be pretty stable because I can form a resonance structure. It's a secondary cation. It's allylic. It then forms, but it's because it's forming an anti-aromatic compound. Anti-aromatic compounds are unstable. They don't want to form. So even though I'm forming something that can that looks like can do resonance structures, it actually doesn't because it's considered anti-aromatic. Okay. So Hückel's rule predicts that the cyclopentadienyl cation is anti-aromatic. In agreement with this prediction, the cyclopentadienyl cation is not easily formed. So this was proof that about Hückel's rule, that in doing something like this, you can't actually form that compound because it's anti-aromatic. So this proves anti-aromatic compounds aren't stable. Okay, here's the resonance form of the cyclopentadienyl anions. That's what's making it stable. Here's also the resonance of the cation, but it says here the resonance picture gives a misleading suggestion of stability, right? Hey, this plus charge is resonating around my molecule. Well, it's anti-aromatic, so this doesn't even happen. It looks like it will happen, but that doesn't even happen. Okay. Then you can get to a 7-membered ring, cycloheptatrienyl compounds. What do you think? Do you think this is stable? Do you think this will form? If you take this alcohol, add acid to it, will this compound form? Take a second to think about it. The answer is yes, because this compound is aromatic. How's it aromatic? 2, 4, 6, 6 pi electrons. Okay, assuming it's planar, which we are assuming it's planar, because you're not told otherwise, this is actually a stable compound. All right, so cyclopentadienyl cation has 6 pi electrons and an empty p orbital, is easily formed, and the reason is because it's an aromatic compound. Okay, and here is the resonance form. What's interesting is they show you the anion form, but how many pi electrons are in the anion? 8, exactly. So not very stable because it's anti-aromatic.